Alright, so where we left off last class was we left off on this sheet right here. We started off with the first two examples. We finished off the first two examples, and now we're going to continue with this third example right here. Whenever we're doing this stuff, again, the topic of chapter 9 is two samples. So whenever we're trying to say something about a parameter, or specifically about two parameters that come from two different populations, so one parameter from each different population. We looked at our formula sheet last class. Here's a portion of our formula sheet that we're going to be dealing with. And again, the main concept that's boiling down to here for these is to see whether or not we have independent samples or if we have paired samples. The samples are going to be considered to be independent if we're taking one sample from one group and another sample from another group. However, they're paired samples if we're taking samples from the exact same group. If we have independent samples, then one of the things that we have to ask ourselves is, are each one of these sample sizes greater than or equal to 30? If they're both greater than or equal to 30, we're going to be using this formula. If one of them or both of them is less than 30, then here we're going to be using these formulas. Whereas if we're dealing with paired samples, the only formulas that we're going to use are these over here. Again, you really don't need to worry about proportions for two populations. We're not going to do an example of that here today, but we are going to continue with these examples right here. So let's carry on with example number 3. In example number 3, it says 6 randomly selected students took an IQ test, and the next day they took a very similar IQ test B. Their scores are shown in the table below. So we have these 6 students, and here IQ test A and IQ test B, and here are the scores for each one of those students. It says, let D be equal to test score A minus test score B, and denote by mu D the mean of their differences. It was already calculated from the above table that D bar is equal to -1, and S sub D is equal to 2.19. Assume that the scores in test A and test B are normally distributed. So let's briefly jog our memory about, again, what these D's represent. You can think of the D's as the differences between the scores. And here the way that they're calculating out this difference between these scores is it takes test score A minus test score B. So here if we take test score A minus test score B for the first student, we have a difference of 0. Test score A minus test score B for the second student, we have 2. Here it's going to be equal to -1. Is everybody good how I'm getting these values? And then here this is going to be -3. This is going to be -4. And here this difference is going to be 0. Those are the individual differences for each one of the students. Those are the individual values for D. But what we can do is we can take the average of these D values, and if we take the average of these D values, we would simply just add up these 6 values that we just calculated out down here, add them up and divide by 6, and that would be the average difference. That would then be D bar, and they said that if you do that here, you're going to get a D bar equal to -1. So here, -3, -4 is -7, -8. -8 plus 2 is -6. -6 divided by the 6 students. It's just going to give us a D bar of -1. If we calculate out the standard deviation of these 6 values that we just calculated, then it's saying that it's going to come out to 2.19. But we're not going to do the arithmetic for that one right here. Is everybody good with what D stands for, what D bar stands for, and S sub D stands for? Alright, so it's important to realize how they're defining this D, and they're defining it as test A minus test B. But let's go on and try to answer the first question. It says that on average, people score better on the second test than on the first test they take. And it wants us to write our null and our alternative hypotheses. So let's do that. So for question number 3, it's saying for A to write the correct null and the alternative hypothesis. Well, if we did this like we did in the previous problems, and we call this group number 1 and we call this group number 2, then if we're saying that they score better on the second test than on the first test, if it's better than, is that going to be our null hypothesis or the alternative hypothesis? It's alternative because it's strictly greater than. So we're going to say that mu2 is going to be strictly greater than mu1. That's going to become our alternative hypothesis. We don't have another statement for our null hypothesis. So therefore our null hypothesis can either be that mu1 is greater than or equal to mu2, or again our calculations would be exactly the same if we wrote that mu1 is equal to mu2. Again, both of these would be possible answer choices on an exam, because both of these we would have the exact same calculation from, just like we had in Chapter 8. Alright, but again, what we said here is that we want to have our hypotheses written as a parameter and then a math symbol and then a number. So one of the ways that we rewrote this last class was we said that we can rewrite our null and our alternative hypothesis by simply just subtracting mu2 from both sides. So then we're going to get mu1 minus mu2 is greater than or equal to 0, and mu1 minus mu2 is going to be strictly less than 0 for our alternative hypothesis. Or similarly, if we went with these hypotheses over here, we have mu1 minus mu2 is equal to 0, or mu1 minus mu2 is strictly less than 0. So again, here we're simply just saying that test 1 is going to be bigger than test 2, or the test 2 score is going to be higher than the test 1 score. We were given the alternative hypothesis, but we weren't given the null hypothesis. So therefore, either one of these null hypotheses will suffice. The calculations will be the exact same way. But we want to get in the habit of writing this as our parameter, then our math symbol, and then a number, so we can get that way by subtracting mu2 from both sides, just like we did last class. But now there's another thing that I want to highlight in this problem. And let's take another look at this problem. For number 3, is this independent samples or are these paired samples? They're paired. Why are they paired samples? Because we're going to the exact same 6 students twice. And we're taking a measurement from that exact same group twice. So therefore, it's a paired sample. And here's something that we can do additionally with this paired sample. We can rewrite our hypotheses now as the null hypotheses and the alternative hypotheses. Here it's mu1 minus mu2. We can rewrite that as mu sub d for their difference. So here we're going to have mu sub d greater than or equal to 0 for our null, and mu sub d, which is simply just the average difference, is going to be strictly less than. Or again, if we're using these over here, we can have mu sub d is equal to 0 or mu sub d is strictly less than 0. Alright, so everybody good with what I mean with this mu sub d, this difference in the mu's? Alright, and the important thing to keep in mind here is this. Let's go through this little mental exercise here real quick. Let's take a look at how they're defining D, because it's really, really, really important to note how they're defining D. The way that they're defining this difference is to take the first test and subtract the second test from it. So let's think about this here for a second. Here the claim is that you're going to do better on the second test. So therefore the second test is going to have a higher score. And if you're going to take your second test score and subtract it from your first test score, what kind of value is that going to give you? You're close. So if our second test score is supposed to be higher than our first test score, and we're subtracting our second test score from our first test score, D should be negative. Right? Is everybody good that it should be negative? Right? So if our D is going to be negative because test score B is higher than test score A, and we're subtracting test score B from test score A, D is going to be negative, then here this should make sense too, that our average difference is going to be strictly less than 0. Right? That our difference is going to be negative, and our difference then is going to be less than 0. Does that make sense? All right. So that's 3A. That's writing our null and our alternative hypotheses. Each one of these 3 ways is technically a correct way to write our hypothesis. The way that you're probably going to see these hypotheses written is either like this or like this. Again, if we have paired samples, that's when we can rewrite it as mu sub D. If we have independent samples, you cannot rewrite it as mu sub D. If you say, hey, there's no way I'm going to remember that, here's a good way to remember it. The only spot anywhere on our formula sheet right here where it's mentioning anything about little d is for paired samples. Right? This is the only spot here where it has d, here it has a sub d. The only spot where it's mentioning the little d thing is for paired samples. So therefore, the mu sub d, you can only do that for paired samples. One way to think about this is, if you're going to find the difference of stuff, the first measurement minus the second measurement, each first thing has to have a corresponding second thing so you can take the difference. If you have independent samples, you can have different sample sizes. So therefore, it doesn't necessarily mean that each thing is going to have a second thing that you can subtract from. All right. Is everybody good with how to write these null and these alternative hypotheses? Then let's go on to part B. Part B is going to ask us to find our standardized test statistic. All right, so we already know that here, I only copied part of the formula sheet. This is the part of the formula sheet that we're going to be using here today. But up here, this column up here, this is our standardized test statistic. Test statistic. Is everybody good that we're dealing here in this example with paired samples? So therefore, if we're dealing with paired samples, is everybody good then that we're going to use this formula right here to find our standardized test statistic? All right. So part B is asking us to find our standardized test statistic. I'm simply going to copy down that formula from our formula sheet. And here we have this from our formula sheet. So let's fill in some numbers. What's d bar equal to? -1. It tells us that in our problem. I'm going to skip this d naught here for a second. What is SD equal to? 2.19. Again, it tells us that in our problem. And what's our sample size? 6, because we have 6 students. Good. So the only thing that we haven't filled in here yet is d naught. But again, the naught numbers come from our hypotheses, right? Mu naught, p naught. Now we're looking for d naught. So what's the only number that we have in our hypotheses? 0. So here we have the 0, right? Again, like I said last class, chances are that d naught is going to be equal to 0 because it's just asking us to say, hey, one thing is less than the other. If it said one thing was less than the other by some kind of amount, then that amount would simply just go right here. If you remember that d naught is equal to 0, I have yet to see a past common final question where d naught was not 0. So chances are that if you use d naught being equal to 0, chances are you're going to be okay on the past common final exam as well. Yeah, exactly. So if you're just like, oh, I have no idea what d naught is on the final exam, put 0 down, chances are you're going to get it right. But what we're talking about here is the hypothesized difference between these two values. And the hypothesized difference, here we're simply just saying that the average of one is less than the average of the other, right? So all that we're saying here is that one needs to be less than the other. If you subtract them, it should be less than 0. But if you said, hey, what if the average test score of a student on the second exam was at least 20 points less than their first test score? Well, that 20 points now, you're not just saying it needs to be less than it, you're saying it needs to be less than by 20 points. Well, now it's not going to be 0 anymore. It's going to be a 20. Cool. All right. Everybody good with how we got these numbers? If you do these numbers, you should get negative 1.12, which is our standardized test statistic. Part C is asking us to find the rejection region and state our decision at alpha being equal to 0.05. All right, so we need to find the rejection region. How do we go about finding our rejection region? Well, first off, we have to determine how many rejection regions do we have. How many rejection regions do we have here? We have one rejection region on the left or the right. So here, good. So we're always going to look at the alternative hypothesis, see where our rejection region is. But you're right, we're going to put all of alpha into this. But what we want to find is we want to find our rejection region. So we need to find, we're going to be comparing our standardized test statistic to our critical value. So we need to figure out what our critical value is. So are we dealing with a z value here, or are we dealing with t values? T values. So we need to find the t value that corresponds to an alpha of 0.05. And how many degrees of freedom do we have here? 5, right? Because we have 6 students. Our degrees of freedom is little n minus 1. Right? Our degrees of freedom are little n minus 1. We have 6 students. So we're going to have 5 degrees of freedom. So if you come over here to the t table, and you say that we have an alpha of 0.05 with 5 degrees of freedom, then the t value that we're getting is 2.015. Everybody good with 2.015? So therefore here, our critical value is a t value, and we looked up 0.215 in our table. What do you guys think about this 2.015 that we got right here in our picture? What's not good about it? Should be negative, right? Because it's below the mean. So even though our t table is giving us a positive value, keep in mind here that we're looking at our left-hand side critical value, so therefore we should have a negative t value. Right? Good pickup on that. All right, but here's the thing. It's asking us for what our rejection region is, but all that we found out so far is where our rejection region begins, which is our critical value. So therefore, if it's asking us for our rejection region goes all the way down to negative infinity and up to negative 2.015. So therefore, that's our rejection region. Is everybody good with this being our rejection region? Any questions about this? All right, that's question 3. Let's move on to question number 4. All right, so question number 4, there's a couple of tricky parts to question number 4. I left it at the very end for a reason. This is one of the more challenging past common final questions that I've seen. We're going to definitely do the first 2 parts, part A and part B, but we're going to leave C until the very, very end of class. If we have time at the very, very end of class, then we'll backtrack and see C. I don't think that you guys are going to see C, a question like C on the final exam. You're definitely not going to see a question like this on the homework or on your last in-class exam. So we'll leave this one to the very end, just more as gee-whiz information than anything else. All right, but let's read this. It says, an economist wants to test if there is any difference in income between Escambia County and Miami-Dade County in Florida. To do this, she collects random samples of residents from both these counties. The information collected from these samples is tabulated below. Assume that both populations are normally distributed with equal population variances. So then we have these 2 things. Question A then asks us to state the correct hypothesis and test the claim. To test the claim. All right, so this is number 4. 4A wants us to write our null and our alternative hypotheses. For the null and the alternative hypothesis, we're trying to see, is there a difference there a difference means that either they're going to be equal to or they're not going to be equal to. If they're not equal to, there's a difference. And if it's not equal to, then our complement has to be equal to. I should say the contrary. I shouldn't be saying the complement. But I think you guys get the idea. Again, what we're going to say is that we're comparing two population averages. So here we're comparing mu1 to mu2. Everybody good with this step? Any questions about this? All right. Then again, we want to make sure that we're writing our null and our alternative hypothesis as the parameter and then a math symbol and then a number. So we're going to rewrite this as such. And chances are you're going to see this format right here on either your homework or in-class exam or the final exam. Now, again, both of these ways of writing it is completely okay. But if we write it in this way, we can identify what capital D naught is based off of this number right here. All right, any questions about part A? Then part B says, find the value of the standardized test statistic. All right, so let me ask you this. Are we dealing with paired samples or independent samples? Paired. Is everybody good that there's paired? Can you explain why it's not? They're in different counties. So is it paired? It's not paired, right? Cool. So no, I saw some people saying, yeah, I'm cool with it. I saw some people saying, what? So why is this not paired? It's in different counties, right? If we were taking 11 people from Escambia County and then we were saying, oh, wow, it's 36,700 in the sample, let's go back and check that again, and you go back to Escambia County and you take another sample, now that's paired, right? If you're going back and you're taking the same number of people, right, or going back to the same group, right? But here we're not going back to the same group. We're going to a different group. We're going to a different county altogether. So therefore, it's not paired. It's independent samples. Right? Does that make sense? Yeah. Another giveaway for why it shouldn't be paired is here we have different sample sizes. Whenever you have different sample sizes, it's not, well, in this class, you're never going to have different sample sizes if it's paired. All right. So we're dealing with independent samples, and we're trying to find our standardized test statistic. So here we're going to go to independent samples. Now what we have to do is we have to ask ourselves the question is, are both of our sample sizes greater than or equal to 30? No. They're actually both, in fact, smaller than 30. And again, I know I'm repeating myself here, but... Sure. Yeah, the number 3, it's paired. Because we're going to the exact same 6 students twice.
Okay, I see what you're saying.
You good with that?
Yes, okay. And since we got 2 different counties going in 2 different regions in the area for it.
That's right.
Okay.
Whenever you go to the exact same group twice, right, that's when it's going to be paired. And to be even more specific about it is, you have to go back to that exact same group and you're taking everybody that you took the first time, you're also measuring them the second time. So it wouldn't be okay to go to Escambia County one time and take 11 people, and then come back to Escambia County another time and take a different 11 people, right? That's not the concept that we're dealing with in this class. It's possible, but we just need to make sure that we state some exceptions to what we're doing up here. So that's why the easy way for you to remember it is, if you go to the exact same group twice, it's paired. Otherwise, it's independent. Cool. All right. So we already said that we have sample sizes that are less than 30. What I wanted to reiterate one more time is, even if one of these is greater than 30, you still go with this option down here. Because in order to be up here in this top box, both of them need to be greater than or equal to 30. And I said that last class, I just want to reiterate it today again. So therefore, if we're going to find our standardized test statistic, we're going to use this formula right here. All right, is everybody good with that? So let's use that formula. I'm going to copy it down here first. We have t is equal to x bar 1 minus x bar 2 minus d naught divided by the square root of sp squared times 1 over little n1 plus 1 over little n2. All right, let's try to plug in the values that we know. X bar 1 in this problem is equal to what? Okay, 36,700. X bar 2 is? Good, 34,700. And D naught, where do we get D naught from? Our hypothesis. So what's the only number in our hypothesis? 0. Is everybody good that D naught is 0? Everybody good with what I have up here so far? Alright, I'm going to skip this sp squared thing here for a second. And we know that little n1 is equal to 11 and little n2 is equal to 15, so I'm going to fill those in. But we still need to know what sp squared is. And this is something I talked about a little bit last time. Here, whenever we need to know sp squared, it's on this line right here. And I said that it has its own separate line because if we try to squish it in there, it would just jack up our table completely. But now we need to know what sp squared is. So here I'm going to copy down this formula because we first need to calculate out what sp squared is. And again, S stands for our sample standard deviation. When it's squared, it becomes our sample variance. The little p stands for the fact that it's pooled. So this is our pooled sample variance. The formula that we have for it is this, and I'm just copying this down from the formula sheet. Are you guys starting to see why I'm giving you a formula sheet for some of this stuff? Like remembering these formulas would be a bear. All right, but we know the numbers for this. Let's go ahead and plug in the numbers to this. We have little n1 is 11 minus 1 times s1 squared, and s1 squared is 7,800 quantity squared, plus 15 minus 1 times s2 squared, which is 7,375 squared, divided by n1 plus n2 minus 2. If you do this sp squared stuff, you should get 7,552.08. And therefore, that's what we're also going to plug in right here, 7,552.08. Say again? So, let me ask you guys this. Is everybody good with where I'm getting these numbers from back here? The N's and the S's. And is everybody good with where I'm getting these formulas from? And if you're good with where the formulas are coming from, you're good with where the numbers are coming from. It's just a matter of plugging those numbers into this formula and doing this arithmetic. And I know that, doing this arithmetic right here and getting this number is what we wanted to have for sp squared. And that's simply just what we're going to plug in here into our standardized test statistics right now. All right. If you do this, if you plug this in and now you do all this arithmetic up here, that's going to come out to approximately 0.67. Yeah.
Where did you get when you did that second portion right here?
This portion right here?
Yeah, and it gave you that number at the top.
This number right here?
Because you skipped it in the beginning and then you went to that second equation.
Yep.
So we have to do the second equation in order to plug in that number at the top.
That's exactly right. Yep, that's exactly right. So you have to calculate out what SP squared is in order to plug that into this spot right here in your formula. So this standardized test statistic form is actually a really, really long formula. And the same thing with this formula right here, because here we also have SP squared in it. So both those formulas are actually really, really long formulas. All right. Everybody good with B? Where we're getting the numbers from, where we're getting the formulas from? All right, like I said, if we have time at the end of class, we'll come back to question C for number 4. But for right now, I'm going to do something slightly different.